Hi there. So this is the second video for week number 14. Let's continue to talk about and solve the problems in chapter 11. So I'm going to go over example 11-2 today. Let's see. Here we go. Okay, so in the previous video clip, I explained about beam column, the PM interaction diagram, the axial force and bending moment diagram, the domain about the failure mechanism, and we have two different equations depending on the ratio between actual demand and actual capacity, PR and PC. If the ratio is larger than or equal to 0.2 or less than 0.2, we have two different formulation. Okay, so using those background, we're going to solve the second example in chapter 11. So this is example 11-2 in page 362. So the question is this: W 10 by 30 tensile member with no holes, consisting of 50 KSI steel and with L sub B done so for the length of 12 feet. And this member is subjected to the actual service load PD of 30 kips and PL of 50 kips, and the service moments MDX of 20 kip-feet and MLX of 40 kip-feet. If C sub B is equal to 1.0, C sub B, that's the coefficient depending on the moment gradation, right? Is the member satisfactory? Okay, so again, we're gonna treat this member as a beam column because we have both axial force and the bending moment. So the section is given as W 10 by 30. And this is a beam column. We have both. I'd like to draw a straight line. Here we go. It's better. So here we have a member. It is under tension, and here we have PD and PL. So PD is a dead load and PL is a live load for these axial force. And we do have bending moment as well. And those are MD and ML, and about strong axis MDX and MLX. So all those moments and the actual forces are given as this. PD is equal to 30 kips. PL is equal to 50 kips. MDX is given as 20. And then MLX is 40. Okay. And L sub B is the unsupported length, which is 12 feet. And then C sub B value is given as 1.0. So we're gonna use this number for the moment equation. Okay, so again, we're gonna start from this PR-PC ratio, because depending on this value, if this is larger than or equal to 0.2 or less than 0.2, we have two different formulations, right? In the previous, the video clip explained about those. So first thing we have to do is we have to find out this demand and capacity under this axial force. Okay, so let's solve the problem. Let's talk about P sub R first. P sub R, which is the demand, which method that we're going to use. Previous example, I used LRFD, so I'm going to use ASD this time. And the other method solution is going to be available in the textbook. So PR using ASD is going to be PA. And ASD demand calculation is easy because we just add them up, right? So 30 and 50, those are our actual demand in dead load against the dead load and live load. So 30 dead load and live load 50, so it's going to be 80 kips. So this is going to be PR. And let's calculate PC. So PC for W10 by 30 section. So we're gonna we can directly use the value from the steel manual, or we can easily find out Pn over omega against in this case the yielding, because in the problem description it says specifically says tensile member with no holes, right? There's no hole, there's no the bolted connection, so the rupture limit state is not going to be available in this case. So the yielding is going to be the governing failure mechanism, and the yielding for Pn is going to be Fy times Ag and divided by omega factor, and omega is going to be 1.67. So 50 KSI still is used, and then Ag for 10 by 30 section, you can look it up, it is 8.84 inches square divided by 1.67. Then P sub C is going to be 264.7 in kips. So this is P sub R, this is P sub C, so you can easily calculate PR to PC ratio, which is 80 divided by 264.7. I got 0.302, which is larger than 0.2. Okay. So again, in the slide that I gave you, or you can easily find out the equation for beam column connection when PR over PC ratio is larger than 0.2, the corresponding equation looks like this: PR over PC plus 8 over 9. So we have now the coefficient, and there's no 2 in the denominator for this ratio. That's the difference between this equation and the other one. And inside of the bracket, we have MR to MC ratio. MR MC X plus MRY MCY, and that if it is less than or equal to 1.0, then it is going to be satisfactory, right? So we have to calculate this value based on PR to PC ratio. Okay, so let's calculate this. PR, PC, we already got it. So, and MRY and MCY, these are not available in this case because we only have, I would say this entire thing goes to 0. So let's calculate MRX and MCX. MRX is going to be using ASD, it's going to be MA against the x-axis. And then MCX is going to be MN over omega. Okay. So let's calculate this demand first, MAX. Again, when we have the moments is given as the 20 kip feet and 40 kip feet for against the dead load and live load, MAX is equal to what? Just add them up together. So 20 plus 40, that will be 60 kip feet. So that is going to be our moment demand, which is easy. Now the only thing left is this M sub C. Now L sub B is equal to 12 feet. So first of all, we have to double check that this L sub B is going to be larger than L sub P or less than L sub P. L sub P, again, you might remember that for the beam capacity, depending on the unsupported length, so this is L sub B, and it is nominal moment capacity. The first one between the plastic moment, MP. The second one, Mn is equal to C sub B times complex expression inside of the bracket. That is inelastic lateral torsional buckling if L sub B is larger than L sub P but less than L sub R, right? Of course, L sub B is less than L sub P, then our Mn is going to be equal to MP. If LB is larger than or equal to LP but less than LR, then we are following this equation. The third one, elastic lateral torsional buckling equation, it looks way more complicated and we don't need to worry about it. Okay, so you can easily look up the value of L sub P and L sub R from the table in the steel manual. We already went through that a couple of times. So when you look it up, LP for 10 by 30 section is 4.84 in feet, and L sub R, that's the borderline between, let me just put, this is inelastic lateral torsional buckling, and here is elastic lateral torsional buckling. This is plastic reason, right? So L sub R value for 10 by 30 section is 16.1 in feet. And our given L sub B, the unsupported length is 12 feet, right? So I can say that this number is 4.84, this number is 16.1, and our L sub B is somewhere in between here, 12, right? So we have to follow this equation. The entire equation looks like this. M sub n is equal to C sub B times MP minus MR. Just copy the equation quickly. Okay. So I'm gonna give you the equation number from the textbook. But in terms of BF equation, okay, we can use this one. So MP minus, let's see, MP minus MR, and then we have a ratio LB minus LP, LR minus LP. So this is the original equation, and we take this as BF, best friend, right? Then our equation with the factor, so for using ASD, it's gonna be Mn over omega, then we have to everything divided by omega, right? So the value Mn over omega will be equal to C sub B, that's the coefficient, MP over omega minus BF over omega times LB minus LP, right? So that is gonna be our M sub Cx here, right? And C sub B, by the way, is assumed as 1.0, so that value is gonna be, this is gonna be 1.0, easy. So what you need to do is you have to find out MP over omega, BF over omega, because we already know L sub B as 12 feet and L sub P is 4.84. So just look up these two numbers from the AISC manual, which is MP over omega is 91.3. So it's just C sub B is 1.0. So 91.3 is MP over omega minus BF over omega, which is 3.08, and then times L sub B, which is 12, minus L sub P, 4.84. Okay, so when you calculate it, I got 69.2 cubic feet. So that is our capacity down here in the denominator. So this value is going to be now 69.2 cubic feet. So plug in these numbers. PR is going to be 80, PC 264.7 plus 8/9 of 60 divided by 69.2. So when I substitute all the numbers and calculate it, the final value is 1.073, which is larger than 1.0. So it's no good, right? So the final answer is no. This section, W10 by 30 tensile section under these given load, 30 kips of that load in actual 50 kips, 20 kip feet, 40 kip feet, using ASD, it doesn't satisfy the load. Okay, so this is the end of example 11-2. And then we're gonna move on to chapter 12, the connections, the bolted connections. Chapter 12 and chapter 14, I'm gonna combine those two together as connection sections, because chapter 12, the bolted connections, we already talked about it in the tension member, right? So I'm gonna talk more details about the bolt material and the bolt, how we can calculate the capacity of the bolt itself using the AIC manuals. That is gonna be the main part for chapter 12. Chapter 14 is gonna be more kind of informational. So I'm gonna share a couple of video clips about the welded connections and the different types and styles of the welding. And then I'm gonna go over one example problem for chapter 14. And then the last chapter, the composite section, will be left for next week. Okay, so this is the end of chapter, the second video. So thank you and see you later. Bye. Oops.